A very warm welcome to everyone. Hello. We are going to discuss electric potential and potential energy today. And what we will start with is the concept of potential energy of a system of 2-point charges. So, potential energy of a system of 2-point charges. This is what we are starting with. Now let's imagine that we have a system of 2-point charges, Q1 and Q2, placed at a small distance from each other, let's say R. This is Q1 and the second charge is Q2. The distance between these two charges is, let's say, R. Now we're interested in calculating the potential energy of this system of two charges. For the sake of simplicity in our discussion, we'll assume that the charges are both positive. Both these are positive charges and therefore they repel each other. Now to calculate potential energy of this system in this condition, what we'll be doing is we'll need to have a reference level. I'm sure you remember from your earlier classes that potential energy cannot be calculated without having a reference level. So here what we do is we assume that the reference level is R tends to infinity. That is, when the distance between the two charged objects is infinity, then the potential energy is 0. This is the assumption we make to start with. Now, if this is the condition finally, initially of course we assume that the charges are at an infinite distance from each other, and in that condition their potential energy is 0. So what we do is we initially imagine that Q2 is initially at infinity, and in this condition the potential energy is 0. Now what we do is we bring Q2 from infinity all the way up to this point, and in this process the electric field of Q1 performs some work on the charge Q2. Now we'll be calculating that work, and we are very well aware that work done by a conservative force is negative of the change in potential energy, and we'll be using this fact for calculating the potential energy of this system in the final condition here. Now let's look for an intermediate position. Let's say when Q2 is over here at a distance, let's say x. Q2 is at a distance x at this particular instant. Now since the charges are positive, this Q2 experiences a repulsive force. This repulsive force F, of course, has a magnitude given by 1 by 4 pi epsilon naught Q1 Q2 by x square. That's the magnitude of the force experienced by Q2 due to charge Q1. We now consider a very tiny displacement ds over here. This is the force F, this is the tiny displacement ds, and in this tiny displacement there's a small amount of work which gets done. Now that work dW which gets done in this tiny displacement will be F dot ds. Now the angle between F and ds here is 180 degrees or pi radian, and so this is F into ds into cos of 180 degrees. Now cosine or cos of 180 degrees is -1, so this dW here comes out to be minus F times ds. Now look here, this ds is actually a change in x. And what kind of change? This ds tends to decrease the value of x. Since ds is decreasing x, what happens is we replace this ds by minus dx. Now why minus? Because ds is a negative change in x, and therefore ds equals minus of dx. Now if we agree with this, let's proceed further. This dW now comes out to be minus and minus becomes plus. F becomes, F of course is this amount here, 1 by 4 pi epsilon naught q1 q2 by x square into dx. This is dW, the small amount of work done when we displace this charge by ds. Now we'll be calculating the total work done in moving charge q2 from infinity to this position when the distance becomes r. Now to calculate that total work, we have to use a summation or an integration here, and therefore dW will be equal to q1 q2 by 4 pi epsilon naught dx by x square, and the limits for x will be from infinity to r. So limits for x are infinity to r. What we get here is 1 upon 4 pi epsilon naught q1 q2. Now here this is x to the power minus 2 dx, and when you integrate x to the power minus 2 dx, you get x to the power minus 1 by minus 1, limits being infinity to r. So we have this work done equals 1 by 4 pi epsilon naught q1 q2 by x. There's a minus sign because we had minus 1 over here, so we have a minus sign, and the limits are from infinity to r. So work done will be equal to minus 1 upon 4 pi epsilon naught q1 q2, and first we substitute r in place of x, so we have 1 by r, minus we substitute infinity in place of x, so we have 1 by infinity. Of course 1 by infinity is 0, and therefore work done W comes out to be minus 1 upon 4 pi epsilon naught q1 q2 by r. So we have calculated work done here, and with this value of work done now available, we can calculate the potential energy of the system of two charges in this final condition, assuming of course that when Q2 is at infinity, potential energy is 0. That's our reference level. So this work done has come out to be negative, by the way, and that's how it should have been, because force and the motion are in opposite direction. So you should always check the sign of work. That's generally fairly tricky, and so whenever you get a magnitude for work, always ensure that you have the correct sign there, using the directions properly. Now, the initial potential energy of the system when Q2 was at infinity was 0, and the final potential energy is U. So U minus final potential energy minus initial, that's the change in potential energy. And the change in potential energy is negative of work done by the conservative force. So U minus 0 will be, U will be simply equal to negative of this work done. So negative of the work done will be plus 1 by 4 pi epsilon naught Q1 Q2 by R. So we've got this potential energy here, potential energy U of a system of 2-point charges Q1 and Q2 placed at a distance R from each other. Now in this calculation here, where we've calculated U, what happened was that work done was negative because both charges were like charges, so force was repulsive and motion was opposite to the direction of force. Therefore work was negative, and since work was negative, the negative of work turned out to be potential energy and therefore positive. If the charges were unlike charges, the force would have been an attractive force leading to a positive work. And if the work was positive, potential energy would have ended up being negative. Now, this can end up being fairly confusing, especially during an exam scenario, and therefore I have a suggestion for you to make this calculation of potential energy. What you need to do is just substitute both charges with their proper signs in this expression. Now, if you substitute these charges with their proper signs in this expression, if they are both like charges, you will have a positive value, which happens with repulsion. And if they are unlike charges, you will end up with a negative value of potential energy, which is what will happen because of attraction. So Q1 and Q2 are substituted with their proper signs in this expression. So as long as you substitute Q1 and Q2 with their appropriate signs in this expression, you will be completely fine. You will get the correct value of potential energy pretty much automatically if you just substitute the charges with their correct signs. So just an opportunity for you to quickly take a screenshot and then take notes, and now we move on. Now this is the calculation of potential energy for a system of 2-point charges. Now what if we have more than 2-point charges? We have, let's say, 3, 4, 5, 6 or whatever larger number of charges. Then how do we calculate the potential energy? It still remains fairly simple. In case of a system of more than 2 charges, what we do is we calculate potential energies of all the distinct pairs of charges and then simply add them up. So in case of a system of more than 2-point charges, we calculate and add potential energies of all distinct pairs of charges. And that's the simple process of calculation of potential energy if you have a system comprising more than two charges. Now, let's take an example where we do this, and we'll take a kind of a fun example. Think of a cube of edge length A. So we have a cube, and this cube has an edge length A, and now charges are placed on all its vertices. So let's say over here we place charge plus Q, then minus Q here, plus Q, minus Q, and minus Q, plus Q, minus Q, plus Q. Right? Now, we're interested in calculating the potential energy of this system of charges. Now, I'm sure you can probably start to visualize that this is kind of challenging because you have 1, 2, 3, 4, 5, 6, 7, 8 charges, and if you have 8 charges, then you have how many pairs, how many distinct pairs? 8 C2, and that should be 8 into 7 by 2, and that's 28 different pairs. Those of you who are not very conversant with the mathematics of combinations and permutations, what I can suggest is that if you have n different objects, then the number of different pairs can be calculated by the formula n into n minus 1 by 2. Now here n, the number of objects n is 8, and so you have 8 into 7 by 2. That's the number of pairs, which happens to be 28 over here. Now, since you have 28 pairs, you have your task cut out, right? But it's not that much of a problem because a lot of pairs are similar to other pairs. Now, let's first look at the edge pairs of charges on the edges of the cube. Now, let's start with this edge, plus Q and minus Q, and you have minus Q and then plus Q, and plus Q and then minus Q, minus Q and then plus Q. So all the edges have equal and opposite charges placed on them. And we all know that a cube has 12 different edges. In case you're confused, just look at the room you're sitting in, assume it's a cube, and just count the edges, the total number of straight line edges that you have. I'm sure you'll be able to count 12. So we have 12 edge pairs. For each edge pair, the potential energy will be 1 by 4 pi epsilon naught plus Q into minus Q, so it becomes minus Q square by the distance between them, that's A, and you have 12 such pairs. This is the potential energy for one pair. For 12 pairs, this is what we have. So we've accounted for the edge pairs. 12 of these 28 pairs have been accounted for. Now look at the face diagonal pairs, the charges on the face diagonals. So on the face diagonal we have minus Q and minus Q, plus Q and plus Q, and you'll see the same pattern everywhere else on this cube. So the face diagonal pairs of charges are all like charges. So face diagonal pairs will have positive potential energies because you have like charges. When you multiply like charges, you get positive product, and therefore potential energy is positive. So for phase diagonal pairs, well, one pair has a potential energy 1 by 4 pi epsilon naught q square by the distance between two charges on the phase diagonal. Now this is A, and therefore this would be root 2a. That's potential energy of one phase diagonal pair. And how many phase diagonal pairs are there? There are 6 faces of a cube. Again, count the number of walls and also add one floor and one ceiling, and you get the total number of faces in your room, which will count up to 6. So you have 6 faces of the cube. Each face has 2 diagonal pairs, and therefore you have 12 diagonal pairs. Multiply this by 12 and you get potential energy of all the diagonal pairs. And then we are left with, well, we have accounted for 24 pairs, so we are left with 4 pairs, and those 4 pairs would be body diagonal pairs. So body diagonal pairs. There are 4 of them. This charge and this charge, this and this charge and this charge, and then this and this. So you got 4 body diagonal pairs. For these 4 body diagonal pairs, let's calculate the potential energy of one of those pairs, 1 by 4 pi epsilon naught. The charges are opposite. On all body diagonals you have plus q and minus q, plus q, minus q, plus q, minus q. So you have plus q into minus q, so you have a minus q square here, divided by the length of the body diagonal of a cube, which we all know is root 3a, and then we multiply by 4. And after this, all you need to do is add up all these values and you get the potential energy of this system of charges. So even if you have more than 2 charges, you now know how to calculate the potential energy. Now I'll be introducing to you another concept, the concept of electrostatic potential, which is related with potential energy, and in another sense it is a scalar measure of the electric field. Now electric fields can be described using 2 different quantities. One such quantity is electric field intensity, and the other such quantity is electric potential. Electric field intensity is a vector, whereas electric potential is a scalar. So it's a scalar representation of a electric field, and what exactly it is will become clear after a fairly lengthy discussion actually. Let's start with its physical meaning first. Very often in books of physics, they start defining and describing potential mathematically first, and then follow it up with a physical meaning or physical interpretation of potential. But we'll be doing the reverse. We'll first describe the physical meaning of potential and then explore it mathematically, just to make it a little bit easier for you to understand, and the process also will become a little bit shorter. So let's talk of electric potential. This electric potential is represented by V. There is no vector sign, it's a scalar quantity, and how we describe it physically is, we say that electric potential V at a point is the increment Increment is our word for change. Increment in potential energy of the system of charges, of the system of neighboring charges when a unit positive charge is placed at point at the point. Now what I really mean is, let's assume that we've got a system of charges here. This is our system of charges. Now because of this system of charges, the potential at this point P is V. Now what I have just described is that if we have a charge of 1 coulomb or unit charge at infinity, then there's no potential energy associated with it. Now once we bring that 1 coulomb charge to this point and place it over here, the potential energy of the system, which now includes that additional charge, becomes or rather increases by the amount V. I'll repeat the argument. If potential at this point due to this system of charges is V, and we go to infinity, pick up a unit charge and bring it to this point, then the potential energy of the system of charges, which now includes that 1 coulomb charge, increases because of our placement here, increases by 1 coulomb. In other words, if we have a charge Q here at infinity, of course zero potential energy is associated with its presence here. We bring it from infinity all the way up to point P, and when we place it at point P, the potential energy of this system of charges changes by Q times V. So this is the physical meaning of what we call potential. Now we can use this description to calculate the electric potential associated with the presence of one single charge. I just mentioned in the definition we have a system of charges here. That system of charges could very well be a single point charge. In that case, the potential can be quite easily calculated. Imagine that we have a charge Q here, plus Q for simplicity of discussion, and we have a point P here at a distance r from it. Now we go to infinity, bring a plus 1 coulomb charge from infinity to this point, this place, and then calculate the change in potential energy of the system, and that will be the potential of this system. So I've gone to infinity, taken a plus 1 coulomb charge, brought it to point P. Now I calculate the change in potential energy of this system. It will be, the potential energy of the system of two charges, which is now 1 by 4 pi epsilon naught Q times 1 by R. That's the change in potential energy of the system of charges when a plus 1 coulomb charge is brought to this point. This, therefore, is the potential V at the point. So potential V at a point due to a point charge Q in its neighborhood is 1 by 4 pi epsilon naught Q by R. Now if this was a negative charge, this potential energy change would have been negative, and the potential therefore would also have been negative. So in this expression for potential, in this expression for potential, you need to substitute the value of Q along with its appropriate sign, and you get the value of V along with its appropriate sign. So Q must be substituted with its proper sign. So we've understood the physical meaning of potential. Now let me summarize this one more time. If at a particular point the potential is V, and if at that point we place a charge Q, then the potential energy of the system changes by Q times V. And that's the physical meaning of potential. Using this physical meaning, we've calculated the potential of a point charge Q at a distance r from it. If we have a point charge plus Q here, then the change in potential energy of the system, if a plus 1 coulomb charge is brought here, that change in potential energy comes out to be this much, which of course we have defined as the potential. So we have understood a physical meaning of this term potential. Now what we'll be doing is we'll be describing some mathematics associated with the concept of potential. Now see, we have a point charge Q over here, and we are coming up with a mathematical definition of potential. And this is a charge, we need not even have a charge. We're looking at this point and we are interested in calculating the potential here. Now to calculate this potential at this point, what we'll do is we'll go to infinity, pick up a plus 1 coulomb charge and bring it all the way from here to this point and calculate the change in potential energy. That change in potential energy will give us the potential, because when we place a plus 1 coulomb charge at a particular point, the change in potential energy is the potential at the point. So we'll be bringing a 1 coulomb charge from infinity to point P. We'll calculate its potential energy there, and that potential energy will actually be the potential at point P. So we've taken up this 1 coulomb charge at infinity and we are bringing it from infinity all the way up to point P. Let's examine this charge at this point over here. Now when it is over here, this plus 1 coulomb charge, it experiences a force E, the electric field intensity. Force on a unit positive charge equals electric field intensity. We consider now a small displacement dr, and in this small displacement we calculate a small amount of work, dw. That dw is E dot dr, the dot product of force and displacement. That's the small amount of work done in this small displacement. Now total work done from infinity all the way up to P will be the integral of E dot dr from infinity to point P. That's the work done. Now potential energy can be given as negative of this work done, or rather change in potential energy. Now the final potential energy U here minus the initial potential energy at infinity is negative of this work, right? Change in potential energy is negative of work done by a conservative force. So minus of this work, E dot dr from infinity to point P. Now this U is the potential energy associated with the presence of a 1 Coulomb charge at point P, and potential energy associated with the presence of a 1 Coulomb charge at a point is described as potential. So this potential at point P equals minus E dot dr calculated from infinity to point P. So mathematically we can describe potential at a point as negative of work done by the electric field in bringing a unit positive charge from infinity to our given point. So potential at a point is the negative of work done by the electric force or electrostatic force in bringing a unit positive charge from infinity to that point. This is the mathematical definition of potential. Now, you can actually derive the formula for potential at a point due to a point charge using this description, and I'm sure you'll be able to replicate the value that we have already been using for a point charge, but then I leave that for you. Do not wish to do some unnecessary repetition here, so you can make that calculation on your own and check this out for yourself whether you get the same magnitude or not. So here what we've done is we've defined potential at a point in terms of the work done by the electric field on a unit positive charge. Now that we have the definition of potential with us, let's now also define the potential difference between 2 points. Now the difference between potentials at 2 points will again be calculated in terms of this work that we have just described. Let's say we have 2 points. We have A here and we have B here. In this region here, there is some electric field, and therefore the 2 points have different potentials. You can imagine that if we have a charge Q placed here, the distances of the charges are different, and therefore their potentials are different, and therefore there is some difference between their potentials. And it's that potential difference that we are trying to now define. So potential difference between 2 points. These 2 points are A and B. Now let's say in this region of space there is some electric field having a electric field intensity E. Now what we are doing is we are taking a unit positive charge from A to B Therefore, the force on that unit positive charge will be equal to this field. We now consider a tiny displacement dr, and in this small displacement dr, the work dw that gets done on that unit positive charge will be E dot dr. Now the total work done in moving from A to B is E dot dr integrated from A to B. Now as we make this calculation, we calculate this amount of work, we get the change in potential energy for a unit positive charge as it moves from here to here. Remember the definition of potential. It is potential energy associated with the presence of a unit positive charge at a given point. So we are moving a unit positive charge from here to here. The change in potential energy will be the same as change in potential, right? The potential energy associated with a unit positive charge equals its potential. So work done from A to B is E dot dr integrated from A to B. The negative of this work is the change in potential energy. So we have moved from A to B. So potential at B minus potential at A is final potential minus initial potential. Final potential energy of a unit positive charge minus initial potential energy of a unit positive charge as it moves from A to B. This will be equal to the negative of this work done. E dot dr integrated from A to B. So VB minus VA equals E dot dr integrated from A to B. Now, there can be a situation where this is that much easier to calculate. Now, this will be easy to calculate when the electric field is uniform. Now, in a uniform field, if we have 2 points, A and B, separated by a distance d, and let's say in this region of space we have an electric field E directed from A to B. Now in such a scenario, the work done on a unit positive charge as it moves from A to B will be simply E times d, and the negative of this work will be the change in potential VB minus VA. That is final potential minus initial potential. This is the change in potential. Final potential minus initial potential is equal to negative of work done on a unit positive charge as it moves from A to B. I know there are lots of words thrown in over there, and you will perhaps need to repeat these ideas several times before they become perfectly clear. But then in this particular example, this potential change is calculated that much more easily. Now the field was pointing from A towards B, and therefore what we observe is, since VB minus VA is coming out to be negative, what we discover is that as we move in the direction of the field, potential tends to decrease. So as we move along the direction of the field, potential decreases. Of course, conversely, if you move opposite to field, potential will tend to increase. Similarly, if we move perpendicular to a field, there is no change in potential. So this is how we define the difference between potentials at 2 points. Now there is another very interesting set of interpretations regarding potential, and that is about the gradient of potential, the rate at which potential decreases or increases as we move along a certain direction. We'll be doing that interpretation now. We'll be discussing it. Again, we'll be using the definitions and the descriptions we have provided so far. So nothing new here. It's just that we'll be looking at things in a slightly new manner or in a new way. So gradient of potential. Now let's say we have our set of coordinate axes defined here. This is the x-axis, y-axis, the z-axis, and let's say at this location the component of electric field in x direction is Ex, the component of electric field in y direction is Ey, and the component of electric field in the z direction is Ez. Now, let's imagine that we move a tiny distance dx along the x-axis direction. We move a tiny distance dx along the x-axis direction. Then Ex times dx will give us the change in potential, because when we move along x-axis direction there is no change in potential due to Ey and Ez, because we are moving perpendicular to them. Those components do not perform any work. So the x component of the electric field is dV by dx, or actually there will be a negative sign as well, because as you move in the direction of the field potential decreases, there's a negative change in potential, so we have a negative sign, and we have a negative sign here as well. More accurately described, this Ex would actually be minus del V by del X, and similarly Ey would be equal to minus del V by del Y, and Ez would be minus del V by del Z. So this is the relation between field and potential expressed in a differential form. We've already seen the integral form of the relation. We are now looking at a differential form of the relation. So the electric field E at any location can easily be calculated as minus del V by del X I cap plus del V by del Y J cap plus del V by del Z times K cap. Now this means that if you are given the potential as a function of x, y and z, let's say 10x minus 10x square y z, then can you find the electric field as a function of x, y and z? Of course, it's very easily done. Electric field will be equal to minus, now what's del v by del x? Partial derivative of this thing with respect to x will be minus 20 x y z, of course I cap, then del v by del y Del V by del Y gives you minus 10x square Z J cap. Then del V by del Z gives you minus 10x square Y K cap. So the electric field now comes out to be 20xyz I cap plus 10x square z j cap plus 10x square y k cap. So if potential is provided to you as a function of x, y and z, you can always calculate the electric field as a function of x, y and z. So that's the relation between potential and field. And now we move on to a geometrical interpretation of the concept of potential. We have actually already seen that as we move in the direction of the electric field, potential tends to decrease, and if we move perpendicular to the direction of the field, potential remains constant. So to have a geometrical interpretation of potential, we define a very interesting concept, the concept of an equipotential surface. Now, what is an equipotential surface? It's a surface on which potential is constant throughout. Now, let's say let's have a simple example where we'll be able to see this quite clearly. Let's say this is the direction of the electric field and these are our electric field lines, right? So the direction of the electric field here is towards the right. This is the direction of the electric field. Now if we draw a surface here over which potential is constant, what we'll be doing is we'll be moving perpendicular to the electric field like this. Now if we move along this surface, all the time we are moving perpendicular to the electric field, and this surface therefore has same potential throughout, because as you move in a direction perpendicular to the electric field, potential does not change. So along this surface, potential is same throughout. So if electric field is in this direction, let's say this is the x-axis direction, this is y, and the perpendicular to this board is z, then in this case the equipotential surface is a plane surface which is parallel to the yz plane. So in fact, if you ever wish to draw a equipotential surface, all you need to do is follow the electric lines of force. Draw a surface which is perpendicular to all the lines of force everywhere, and you get your equipotential surface. I'll give you a simple example. For example, if we have a positive point charge plus Q, then the electric field lines radiate outward from it, right? Like this. Now, if you are interested in showing an equipotential surface here, what you'll be doing is you'll be drawing a surface to which all these lines are perpendicular. So I start drawing a surface from here, and that surface needs to be such that this line is perpendicular to it. So the surface will curve like this, and as it curves, it needs to stay such that the other lines are also perpendicular to it. So you keep drawing a surface to which all these lines remain perpendicular, and you get an equipotential surface, which in this case will be a spherical surface for which the charged particle is at the center. So if you have a sphere, then all these radial lines will be perpendicular to it, and therefore this is an appropriate equipotential surface. So in this video here, what we have discussed is the concept of potential energy of systems of point charges. From that concept we deduced the concept of potential. We looked at a physical meaning of potential. Potential at a point is the potential energy associated with the presence of a unit positive charge at that point. We studied this physical meaning, and then we had a mathematical definition of potential. Now these concepts kind of look a little far-fetched, or let's say there seem to be a whole lot of mathematics which feels a bit complex. It really is not, and its applications are actually very, very simple. But before we can move on to those applications, you need to review these ideas. There is a need for you to watch this video at least 2 to 3 times, take detailed notes, and then move on to the next video, where we'll be discussing the applications of the concept of potential. But please make sure you view this video several times. One viewing of this video will certainly not be enough. You will not really be able to grasp these concepts, because there is a fair bit of intertwining of physics and the mathematics of it. So it's a bit complex, and therefore I suggest multiple viewings of this video. Take notes, especially of the definitions and the descriptions of the ideas, and make sure you have them on your fingertips before you move on to the next video. Thanks a lot for watching this. Please ensure that your feedback keeps coming. Like, share and subscribe these videos if you enjoy their content and you're able to understand physics. I know some of the content in these videos is fairly difficult to understand, but then there is no other way out. Physics can be simplified to an extent and not beyond. So thank you very much for watching. Keep watching these videos, keep your feedback coming. Thank you very much.